This is the final lecture in 4 lectures that we were presenting on survival analysis. This one will encompass the proportional hazards model. So we're going to first define the model, then we're going to talk about how the hazard ratios are estimated from this, both for dichotomous and continuous independent variables. We're then going to talk about the test of the assumption of the Cox proportional hazards model, and there's going to be a brief discussion about the power and sample size estimation and an example given here. So first of all, when do we use this? Basically, if we have a lot of strata and there's several risk factors of interest, it is a more convenient approach for us to use the Cox proportional hazards model, which is a regression analysis for survival data. It's referred to as the Cox model because D.R. Cox proposed it in 1972, actually. So the proportional hazards model, the driving force of it is the hazard, the way in which the hazard is modeled. That is to say that H of t is composed of 2 parts. H naught of t, which is the baseline hazard at time t, and then this collection, this function of e to the beta 1 sub 1 plus beta 2 of x2 plus all of this equation you're seeing here, which is a collection of independent variables. The hypothesis test for the coefficients is very handy. It basically ends up taking the point estimate you get from the regression result, divided by the standard error for that same estimate. You just looks like the z critical value, and we compare this in the normal way to determine the exact p-value. So if we had a dichotomous independent variable where, so for instance, xa x sub j is equal to 1 if the characteristic is present and 0 if it's absent. Under the Cox proportional hazards model, looking at that h of t function, we would be able to define this function in both ways where x sub j is 1 and x sub j is 0. In particular, anytime we see x sub j, when it's 1, we give it a 1. X sub j is, when x sub j is 0, 0 is in place. Therefore, this beta sub j goes away, and we're left with just beta sub j1. And in particular, when we look at a ratio of these two things, we are left only with the exponentiation of beta sub j because all of the other things cancel out. So the above ratio represents the ratio of hazards of 2 people, one with the risk factor present and the other with the risk factor absent, given that both people have the same values for all the other covariates. The hazard ratio, or the relative hazard, can be interpreted as the instantaneous relative risk of an event per unit time for a person with the risk factor present compared with a person with the risk factor absent, given both individuals have survived to time t and are the same on all other covariants. So we can also calculate a confidence interval for the hazard ratio, and this is done in the following way. We exponentiate c sub 1 and c sub 2 for the upper and lower bounds of the confidence interval, and c sub 1 and c sub 2 are simply the point estimate plus or minus the z critical times the standard error for the point estimate. For continuous independent variables, and suppose that the continuous independent variable was this x sub j again, really what the difference between x sub j between 2 people would be some delta on the jth independent value. And so the quantity of the exponentiation of the delta beta sub j represents the hazard ratio between these 2 individuals. The confidence interval estimation for this is done very much in the same way. We have, again, the exponentiation of the upper and lower bound of the c sub 1 and c sub 2, constituting the upper and lower bound of the confidence interval. And c sub 1 and c sub 2 are simply whatever that value of change is, beta sub j plus or minus the z minus 1 over alpha 2 standard error of the beta sub j calculation. So the first example that they give you is 14.37 of the textbook, and the fitted proportional hazards model output is given in table 14.19. We can assess the statistical significance based on this result. And if you look at the z critical value for this, or the wall test statistic value, we see 2.38 and a p-value of 0.017. which means for that particular variable of interest, which was the CO concentration, that we would say there's a significant effect of CO concentration on the hazard or risk of recidivism. With the higher the CO2 concentration, the higher the hazard. If we wanted to test this, the second variable of interest is beta sub 2, which corresponds to age. We would see that a p-value of 0.386 indicates that there is no significant effect of age on hazard. What is the relative risk or hazard ratio if two people of the same sex who differ by 1 unit on an adjusted log base 10 of CO2 occurs? We say that CO2, since CO2 is a continuous factor, as we defined it before, the relative risk for the continuous variable is the exponentiation of this delta times beta j. So the delta of interest here is 1 unit, and beta sub 1 is 0.833, which means our calculation results with a relative risk of 2.30. This means, given both the people have not started smoking up to time t, the person with 1 more unit of CO2 is 2.3 times more likely to start smoking than the other person. So we use the Cox proportional hazards model to estimate the hazard ratio, the confidence interval of the hazard ratio, and we compare survival curve for subjects receiving a high dose of a particular vitamin versus a low dose of vitamin A. And we base this on what we're seeing in table 14.12. What are we going to do here? We have a covariate now where we dictate, it's dichotomous, 1 if it's high dose, 0 if it's low dose, which means the high dose model, when we have beta 1 associated with this variable of interest, we have H naught plus exponentiation of beta 1, and we have H sub naught for the low dose variable, and the ratio of these two yields the exponentiation of beta sub 1, and we estimate beta sub 1 given the output is minus 0.35, and we see then that the hazard ratio is e to the minus of this, or 0.703. How do we interpret that? It means that the failure rate at any point of time is approximately 30% lower for patients on high dose than those of patients on low dose. The hazard ratio is also significant because the p-value is 0.03 in the same table that we see there. The 95% interval is basically, again, the calculation of the lower bound would be the point estimate of interest times that margin, the minus 1.96 times 0.163, which is the standard error about that, yielding minus 0.672 as the C1. We're not done yet. We have to also calculate C2 and exponentiate both the upper and lower bound. We do this here by showing that C2 is minus 0.032, and the exponentiation of both of the upper and lower bound yields that the corresponding confidence interval for the hazard ratio lands between 0.51 and 0.97. The estimates for the survival probabilities and curve. The estimates of survival probabilities for high dose and low dose are given in table 14.2, where the observations, the first 7 observations, correspond to survival probabilities for high dose, and 8 through 14 corresponds to low dose. We then look at the curve presented in 14.8, and what we need to pay attention to now is the assumption of the main assumption of the Cox proportional hazard model, which is to assume that the hazard ratio of the covariates remain constant over time. We can test this assumption by introducing a cross-product term of a specific variable of interest, whatever the variable we're looking at, times time into the model and test for statistical significance. This is often referred to as a time-dependent covariate. If a violation of the proportional hazards assumption is found, then the most appropriate thing to do then is to not do the Cox proportional hazards model and to present separate analysis for the different periods of time. An example of this is 14.40, and the experiment was designed to test the efficacy of 325 milligrams of aspirin to prevent heart disease and 50 milligrams of beta-carotene taken every day to prevent cancer. The variables used for risk prediction of myocardial infarction on this endpoint is age, BMI, current smoking, and history of cholesterol and history of diabetes. Assuming that the hazard ratio for the baseline covariates remained the same over the entire study period, we would be able to use the Cox proportional hazards model. If that assumption held, we would be reading and interpreting the output of the first column in table 14.22. But we see that all the covariates have significant effect on the hazard ratio in this column. Some of the covariates, though, we know can change over time, so we want to check first to see if the hazard ratio itself remains constant over time. To check the assumption, a second model is fitted with the interaction of time and the output, and that is the second column of the same table, 14.22. We see there is an interaction between time and cholesterol, and also an interaction between time and diabetes. Both of these are significant. Besides, the hazard ratio of each of these variables is less than 1, which means the effect of high cholesterol and diabetes is much stronger at the beginning of the study and weaker towards the end. Since we have now found that the Cox proportional hazards assumption is violated, we now need to show this separate analysis for a different period of time. In table 14.23, we see the output for separate analysis presented, and the first column represents the analysis for the first 10 years, and the second column is the last 10 years. From the table, then, we see that the effect of high cholesterol and diabetes is higher in the first 10 years than the last 10 years of study, and that's an important description of the data. We now move on to the estimation of power for the comparison of survival curves and between two groups under the Cox proportional hazards model. We begin with some basic notation. We have an experimental group and a control group. We have an N sub 1 and N sub 2 for the numbers of participants in each of those two groups, and T represents the maximum follow-up time. We want to compare the survival curves between the experimental group and the control group, and in particular that means determining whether the incident rate ratio is 1 versus it being something other than 1. An incident rate ratio is the underlying hazard ratio for the E group versus the C group. If the ratio of the participants in the group 1 compared with group 2 is K equal to N sub 1 over N sub 2, then this K value, and we'll talk about M in a second, K value represented in here. Typically K is 1, but that doesn't have to be the case, and if it is, then this would reduce to just M, the absolute difference between the incident rate ratio and 1. Note 2, we are taking minus the Z sub 1 minus alpha over 2. This is the power calculation. M is the number of events, expected number of events over both of the groups, and these again are calculated using the probability of the expected failure in each of the two groups. We see them calculated here, and the bits and pieces of the power calculation we had seen before in previous slides. And recall too that the lambda sub I is the approximate hazard at time I in the C group, and the lambda sub IE is the approximate hazard of time I in the E group. The delta sub I is the probability a participant is censored at time I given he was followed up to time I and has not yet failed. The example presented in the text is 14.30. Using the data in table 14.12, the example is that we suppose an investigator wants to repeat the study to be sure the protective effect of vitamin A was not some random occurrence. The study design of the new study would have only 2 vitamin A treatment groups, one with 15,000 IU per day and the other with 75. The investigator feels they can recruit 200 patients in each group who were not involved with the previous study. Therefore, the participants will be enrolled for a 2-year period, followed for a maximum of 6 years. The question of interest is how much power does the study have to detect a relative risk of 0.7, where the endpoint is a 50% decline in ERG amplitude comparing the 15,000 per unit IU per day group with the 75 IU per day group. The solution is that since we're looking for, or we have an incident rate ratio of 0.7, and we have an alpha predefined 0.05, giving us a z critical of 1.96. We expect to get 200 in each of the two groups. We expect 200 participants. Our ratio of allocation is 1, and we have a follow-up time of 6 years. In this example, we are going to assume that the control is 75 and that the experimental is the 15,000 IUs per day. We want to then compute the probability of each of the two groups so that we can get to those expected numbers. The incident, we need to take the alpha sub I, the incident rate ratio of the lambda sub I for both the control and the experimental, and that delta sub I. The computations are given in table 14.24 of the textbook. We will show here how the values were computed in that table. This is slightly tedious but worth going through. For the column that is used to give us the estimates of the lambda sub I, so this is the measurement for group C, which is the 75 units per day. For row 1, we have 8 over 182. Note that means that we have 8 failures in the total of 182 available. In row 2, we have 13 failures of a total of 174 available, which is 0.0747. We keep going down on each of the rows. They are calculated in a similar way. To get the column for the incident rate ratio of the lambda sub I, it's basically the multiplication of the initial row of 0.7 and the column of lambda sub I. So 0.7 times 0.0440 gets us 0.0308, and so on and so on. For the delta sub I column, it's 0 for row 0. Row sub 1 is 0 divided by the 82 minus 8. Row 2 is the 3 divided by 174 minus 13. And note the reason for this is that 3 were censored in this time interval, and that 174 minus 13 have not yet failed. In row 3, we're looking at 2 over 158 minus 21, and the remaining rows are done in the same manner. Column A sub 1, we can't compute, okay, because of the 0, obviously. Row 1, we have A sub I is equal to 1 minus the lambda sub I, which is 1 minus 0, that gets us 1. Row 2, which starts to get interesting, is this 1 minus lambda sub 0 times 1 minus lambda sub 1. So we're seeing the combination of each of the previous rows calculation being involved, and the following rows are computed in the similar way. To find the A sub i's, we use the formula as mentioned below. The stuff in column B sub I is again 0. The row 0 cannot be computed. Row 1, however, is 1 minus that value we calculated of incident rate ratio times lambda sub 0. We will be using the column of the incident rate ratio lambda sub I to compute B sub 1. So we have 1 minus this incident rate ratio lambda sub 0 times the lambda of incident 1 minus the incident rate ratio of lambda sub I 1. So that gets us 0.96, continuing on in the same manner. C is done using the deltas, the 1 minus deltas, and then again this 1 minus delta sub 0, 1 minus delta sub 1. D sub i's are done in much the same way, although we now use the lambda sub I times the A times the column C sub i's, and we calculate these in each of the rows in a similar way. E is the incident rate ratio lambda sub I times column B sub I, C sub I, and multiplying the respective columns we would get E. So we then sum the P sub C and P sub E's. We get 0.48 for the P sub C, and we get 0.37 for the P sub E. That's what gets us to the M, which is the magic number we're looking for to plug into the power calculation. So now we have N sub 1, P sub E, plus N sub 2, and P times P sub C, which gets us to 171.9. We have 171.9 times k, which was 1. The difference in 0.7 minus 1, and the critical value of 1.96, getting us to a power of 0.638. If we wanted to compare the survival curves between the experimental group and the control group in a clinical trial, where the ratio of participants in group E to group C is given by K, and the maximum length of follow-up time is T, we postulate that the hazard ratio of an incident rate ratio for group E compared with group C, and we wish to conduct a two-sided test with a significant level of alpha, we then look at the number of participants needed in each group to achieve a power of 1 minus beta is equal to n sub 1 and n sub 2 separately, m times k divided by k p sub e plus p sub c, where m is 1 over k, and k times the incident rate ratio plus 1 divided by incident rate ratio minus 1 squared, and the z critical for 1 minus alpha over 2, and the z 1 minus beta all squared. If we want to estimate the required number of participants needed in each group to achieve an 80% power for the study in the previous example, we look at the p sub c and the p sub c calculated earlier. Note that again our k is equal to 1, the equal allocation. The m value for this would then be calculated as 251.8. We then go back to our formulas for n sub 1 and n sub 2. We take the value of m, the 251.8, times 1 divided by 1 times 0.3707 added to the 0.4890, getting us 293, and we look at n sub 2 is equal also to 293. Therefore, we need 293 participants in each group for a total of 586 to achieve a 80% power. That is seemingly very tedious calculation, but worthwhile doing at least once to understand both the nature of the incident rate ratio calculation for effect to determine the estimated probability within the experimental and control group, the inclusion of the allocation criteria, and the calculation of total sample size per experimental and control group. This concludes our lecture on the Cox proportional hazards model, which is the final lecture in the survival analysis, chapter 14, Rossner.